Hi, it is lecture two now. Hello, good to see you. You have your study guide? Remember, study guide looks something like this, right? Kind of like this. That's the second page. Study guide might look something like this on the first page. Make sure you have your study guide ready. Are you ready? All right. Pause the video if you want. Get the study guide, get ready, and we will start with lecture two. Okay. Now, with lecture two, remember, first, let's start by going back to the syllabus. And you'll see that question one, right? Science, scientific knowledge, and you have a whole bunch of questions underneath. What is physics and why should I care? Physics is a science, right? Amongst many other things. Now, what is a science? And what makes science what it is? What makes it different from non science? This is actually very important, and you might have heard a lecture along these lines at some point in your past education, but it's really important that you hear it again, I think. And you might see some twists that you didn't see before because science is complicated. You've probably learned about something called the scientific method, right? And it's been part of your education for a very, very long time. But it's not as simple as you usually learn in a course about what is the scientific method because science is complicated. It's a human process. And as with any process, if you simplify the explanation too much, it leads to misunderstandings. And so a lot of what's happening now out there in communicating science, things that are so important in our society, aren't quite getting out there as well as they could. And I hope that this lecture two gives you some sense of what that means and what the science is and all the words involved and things like that. Okay? So, a lot of this lecture, just so you know, has to do with the work that Dr. Eugenie Scott give. She does a lot of work about science education, science communication, things like that, how to distinguish between what is scientific and what is not, Dr. Eugenie Scott. So go take a look at some of her work, and you'll no doubt see a bunch of what I'm describing here in her lectures and in her conversations, lecture notes, writings, etc. Okay, so let me give you the sense. There are a lot of words, right? And right on the syllabus, a lot of different words. Now, I use backs of envelopes. There's a famous thing in science called the back of the envelope calculation. And I just use back of the envelope because it's a good way to save paper and to use junk mail for something other than junk. Anyway, these are just some of the words, right, that you've heard tossed around: facts, law, data, guessing. Yeah, is a guess as good as a theory? Is a theory just a guess? Hypothesis, what is that? And then there are these things: experiment, observation, simulation. How does this all fit together in an explanation of what science is? Well, let's get started. Let's start by giving the sense: what is a fact? A lot of times you hear, oh, it is a fact that this, that, and the other, right? And yes, facts, even if they're not faked, right? Even if they're not purposely designed to deceive, facts are just that: pieces of information that you get from observing or looking at or seeing what's going on in the world. Okay. Very simple example I have here: an orange. Hey, what happens if I drop this orange? Let's say I hold the orange right up here and I let it go. And I put my hand over here. Okay. And I let it go. It falls. Hmm. Okay. That's good to know. That is a fact. If I take an orange and I suspend it in the air in my hand and I let it go, it falls. All right, that's a fact. What else is a fact? Oh, I have here a marker. Yeah. If I take this marker and I hold it in the air and then I let it go, it falls. Hey, that's another fact, right? If I take this little distorted bottle of water, this was sitting outside at one point, and so therefore it got all kind of squishy because it got cold and got hot. Excuse me. If I take this bottle of water and I take it over here and I hold it midair and I drop it, it falls. Hey, there's a lot of fact. All these facts, they seem to form a pattern, don't they? Right? There are a lot of facts in this world, right? If I turn that light switch on, then that light bulb comes on. If I drop this object, it falls. If I toss this object that way, it goes up and then comes back down while it goes horizontal. There's lots and lots of facts in this world. And so a fact is very important, but it's only a piece of information. What we want to do is make sense of facts, right? So therein lies a really important point. Excuse me. Facts organize into patterns. The fact that all those things, all the facts, that all those things that I hold up in air and let go drops means that there's some sort of pattern, something in nature that creates a thing that happens over and over again. That's a law of nature. Laws of nature are things that you observe that follow specific patterns. Okay, that's a law of nature. Now, laws of nature can be very general, right? When I hold it, it drops. Yeah. Or they can become very specific. How? This is how you do it. If you take your facts and you tweak them just a little, you improve on them. Fact 2.0. Okay. That's called data. DATA, right? That's the word here. Facts, laws, data. A point of data, okay, it's called a datum, actually. So data is plural. So, that's for your English teachers if you're interested in that. Data is when you gather a fact carefully and you have information about that fact that's more than just a simple observation. So, for example, a piece of data might be if I hold this orange exactly 30 centimeters above my hand here, right, and I let it go, it will fall for exactly a certain number of seconds before it hits. That's data, right? So you have to get a sense, first of all, the difference between facts and data is an extra piece of information, usually something numerical, something mathematical, right? And it's very powerful to have that extra piece of information. And part of the reason math is so important in our lives is because it transforms proper, good facts into useful data from which we can then gather more information about how the universe works. We can then start using that information, not just generally, but with more knowledge, with more power, with more effectiveness. So that's your transformation from facts to data. And if you notice a law of nature that follows fact patterns, right? Then what is a law of nature when you have data? Then you've got formulas. Then you've got mathematical reproducibility. So if I know, for example, I hold this 30 centimeters up and I drop it and it takes a certain amount of time. Then if I hold it, say, 40 centimeters up and drop it, takes another amount of time. Then I hold it 50 centimeters up and I drop it and it takes a certain amount of time. I can then map out something that allows me to predict, oh, if I drop it from 60 centimeters, it'll take this much time. If I drop it from 70, it'll take that much time. If I drop it from 500 feet, it will take a certain amount of time. That's the power of using data to make a law of nature, because then you can actually make that a predictive, powerful, additional piece of knowledge that you can use. Okay? Good. So far, so good. So that's where your laws of nature come from, facts or data in the patterns that we can reproduce either mathematically, numerically, or we reproduce just with observations and see patterns appear. Now, then the next question that we all humans, always asking all the time, right? Why? Why does it work? Why does stuff fall exactly in this pattern? Why are these laws of nature, these formulae that describe things like how fast things fall, what direction they go, how long it takes, why do they work? That is where you're starting to get complicated. This is where science really shines. Because what happened is that hundreds of years ago, okay, a guy named Galileo Galilei, great guy. He did all kinds of really interesting things. He's in Italy. We'll learn more about him later on in the semester. Galileo Galilei basically said, look, as awesome as it is to think of ideas about why, philosophical ideas, theories of beauty and ethics and things like that, when we're talking about the natural world, we can create theories that are based on facts. Things that will happen regardless of how beautiful or ugly we think they are, or how moral or how ethical they are. The bottom line is nature will follow certain ideas. And so you have to Just gotta prove them in a different kind of philosophical realm than proving things like other kinds of philosophy, happiness, social contracts, economic theories, those kinds of things. So the science is really what's key here. That's what separates the scientific ideas from the non scientific ideas. Now, non scientific ideas are not necessarily wrong, right? This is something that's very important. A lot of us think, oh, well, scientists, if everything is not scientific, it just must be wrong. They must be anti non science. That is not true. There are many scientists who believe in things that are non scientific. Okay. There are certain spiritual beliefs, for example, or wisdom traditions, religions, things like that. Many of them do not have a scientific basis, but they still are powerful and important. So scientists are not necessarily not religious. Scientists are not necessarily not spiritual. Scientists are not necessarily not believing things that they can't prove scientifically. But it is different. And that's where you know the difference is involved. Okay, so picture, if you will, a situation where you have two branches. You come up with an idea. Why does something work? Okay, we call it a guess. Educated guess might be a hypothesis. All right, that's a word that you've heard before, right? It's based on Greek for like, it's an idea. We're not really sure if it's true. So you have a hypothesis, an idea. Now, if that hypothesis can be confirmed, if you can show that it is true, then it might be scientific or unscientific. But if you can show that it's false, that is when it's scientific. You see, you have to be able to prove something is wrong in order for it to be truly scientific. You can prove something is right. There's always ways to prove things are right, at least some of the time, right? But a law of nature is right probably all of the time based on what you see. Why is it all the time? If you can prove that at one point your idea, your guess, your hypothesis, your way of proving or showing why this law of nature works, if you can show that it's wrong, that's where your power is. Because if someone comes along and says, well, I show that you're wrong, then you know that your thesis, your hypothesis, your theory isn't quite correct. And that's okay, right? Just means you have to fix it. You have to get it right. But the ability to falsify, to test your hypothesis is what makes it potentially scientific. Okay. So far, so good? All right. We're drawing all this. So you have the ability to prove it wrong makes it scientific. If you don't have the ability to prove it wrong, either because it's impossible to prove it wrong, either you make it impossible by the very nature, if it's you have to just believe it to take it on faith or something, then it's non-scientific. But it might still be right, just not scientific. Make sense? Okay. So how do you show whether or not your hypothesis, which is falsifiable, which can be proven wrong, is actually right? Well, what you do is you make some predictions, you make some thought processes, and then you test them. You test them using hypotheses. Um, no, actually, you test them using experiments through observations. You take a telescope and you look up in the sky and you see if what you predict is true of this star and that star and that star are true. Or you set up a laboratory and you take things of different weights and you drop them or you roll them or you move them in whatever way in different methods or at different distances and so forth and show that your hypothesis is right or wrong. It is that extra process of study, right, that makes something scientific if it's shown to be true. Finally, there is recently, in the past few decades, thanks to technology, right, there is recently now a new way to test your hypothesis, and that's called a scientific simulation. You make something that represents a physical system, even if you can't touch that physical system, right? Even if you can't quite get it right. For example, there is a way where you can use a computer to run the laws of physics through mathematically and computer programming over long periods of time. And then you can simulate what you think should happen to, say, a star or to a solar system. Where are all the objects going to be? Or something like a galaxy, or even something as small as a DNA molecule, right? Or a protein. Will it fold properly? Will it do its thing based on the laws of physics given enough time in this computer simulation? You're still running the laws of physics in this computer. You're simulating them because you can't quite do them in real life. But that's a kind of test as well. So this kind of testing is all extremely important. So again, to review, you have simulations, you have experimentation, you have observation. All of these things are designed to see if you are right or if you are wrong. Okay. In your lab classes, if you do an experiment and you get the wrong answer, that's okay. I want you to feel comfortable about that, by the way. I know this is the lecture part, but I want you to feel comfortable. If you're doing your lab and the answer isn't quite right, that's okay. Find out why. Have you falsified the hypothesis? Or have you found something new? Or have you seen a little something or another that's a little bit different? That's cool. That's actually okay. In fact, it is the foundation of some of the most important discoveries in the history of science. So, if and only if you make your predictions, it could be falsified or it could be confirmed. And then you do your tests. And then it is confirmed and not falsified. Yay! Then at last, your hypothesis, your educated guess, becomes a scientific theory. Okay, so let's review. I actually drew something over here, another back of the envelope calculation. Scientific theory, right? Turns out that scientific theories are very, very important. Those are the foundations of the kinds of things we want to learn, not just facts, not just laws, but the scientific theories tell you why. They explain the laws in a context that makes sense, and that is why they are so important. You can memorize all the laws you want, and you can solve problems and so forth, but that's just mechanical. That's not understanding how the world, how the universe, how the human body works. That's just sort of it does work that way. Why is your scientific theory? Okay, so I drew this little thing over here. Again, you can find things like this all throughout the internet that are like fancy and spiffy. And again, you can go look at Eugenie Scott's work um, about this. Eugenie, Eugenie, last name Scott, Scott. Now look online for something along these lines. Not quite as messy as what I drew them, but this is kind of what it looks like. You have facts all over the place, right? Lots and lots of facts. But when facts form patterns, then they become laws. You see the laws of nature represented themselves. Now, then you do lots of work to gather and interpret data, to understand these laws, see how they work. And then from there, you make an educated guess, a hypothesis as to why they work. What is the rule? What are the pattern creating things? That's your hypothesis. If then you attempt to falsify, right? You try to show if it's true or false through predictions and then trying to experiment and observe and simulate to see if your predictions are true. That's your heading toward the scientific theory. If you do your prediction, you say, I predict this will happen if I do this experiment, and then you do the experiment, it doesn't happen. Oops. That's okay. Try again. Come back to make a new hypothesis or improve your hypothesis. That's okay. That's part of science. It's part of the process of learning what's true. For every correct scientific theory that is the hallmark of um, our society today, there are dozens, hundreds, thousands of incorrect hypotheses. Were all of those scientists like stupid, or were they useless? Were they wastes? No, they were all extremely important. They might have been wrong in that instance, but they contributed to a meaningful and valuable and possibly like society changing correct answer. So that's okay. So only if you get the scientific theory right, you got to go all the way up here. Then you finally have your scientific theory because you have attempted to falsify it, but instead of falsifying your hypothesis, you confirmed it. That makes your theory scientific. If you do not do this, if you just say something is true, That's an unscientific theory. Doesn't mean, again, it doesn't mean it's wrong. It doesn't mean it's bad. An unscientific theory, for example, might be something like, well, something that I believe in, right? True love conquers all. Uh, does true love conquer all? Maybe, maybe not. I mean, there's plenty of examples of it not conquering all, but like, what is all, right? Is all like all of society eventually, whatever? I mean, and what's true love? What do we mean by that? So, I mean, it's not really testable hypothetically, right? You can't test it with an experiment observation. You can test pieces of that idea, but the idea true love conquers all, it's unscientific. Does that mean it's bad? No, I think it's great. I think we all believed that true love conquers all. And if we all worked at it, and if we used it in our lives, maybe the world will be a better place. I'm cool with that, right? That doesn't mean it's bad, doesn't mean it's wrong. It's just unscientific. And if you know the difference, then you are way ahead in the game of understanding and improving your life through science. Okay, so that's the thing you want to do. Now, two more points. Point one, just because you got your scientific theory doesn't mean you're done. In other words, if you're a scientist and you have gone through all these steps and you have confirmed your scientific theory, is it over? Ha! It ain't over. Was it over when the Germans bombed Pearl Harbor? Germans. Forget it. He's on a roll. No, it ain't over. If anybody got that video movie cultural reference, put it down in your study guide. Bonus points. Anyway, it's not over. In other words, I'm going to draw a line now. Let's see if I can do this backwards on this screen. The scientific theory is not over because you got to go all the way back. Every time you finish a scientific theory, you have to go back to collecting facts. That scientific theory becomes like one of these big facts, a piece of information that helps explain all other facts in the future. And it turns out that it might not be perfect. In other words, you might wind up with a scientific theory that's correct, like, 90% of the time, or based on what you got at that moment, right? And so it becomes part of these fact spaces. But then you might find out someday, as you are coming back, right? You get this down, you come down to the facts here, that somehow it's not right. Parts of your scientific theory may not be correct. You may wind up imperfect. And you got to go through the whole process again to come up, back and forth and back and forth. So this is a cycle. It never ends. Scientific theories wind up looking like Swiss cheese sometimes, or they wind up being a little bit weird. You're like, wait, a scientific theory? I'll use another back of the envelope here. Let's say I have a beautiful scientific theory that works super well. All right, yeah, that's a beautiful scientific theory. But then it turns out the scientific theory isn't quite perfect. Oh no. Let's say this theory has a hole in it. Uh-oh, it didn't quite work, right? For some experiment, it didn't work. Uh-oh, there's a hole in the theory. Oh no. And then someone finds another hole in the theory and another hole. And before you know it, you wind up with all kinds of holes. I mean, this is a really tough situation now. Uh-oh. Do you throw away the whole theory? No. These holes exist in the theory, it's true, but they're not necessarily indicative of the fact that your theory is wrong. It just means that maybe your theory is incomplete. Maybe there's actually more to the theory than you thought. So I'm going to draw this here. And what you thought was a theory that was totally correct turns out only to be a piece of a bigger theory. And the reason those holes are there, right? This is the big theory, ho, 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 like that, right? You have a big theory, and what you found was the little theory. And all the holes in the theory weren't actually holes at all in the big theory, but they were like pieces of the big theory, which you didn't quite understand because you didn't have all the data yet, because there was more stuff to the theory. So theories can be inside theories, and they can start encompassing other theories. They can improve on different theories. There's all kinds of examples of that. That's really, really, really important. Okay, for example, I'll give you one example. I'll use biology. Okay. Um, Charles Darwin, in the mid 1800s, figured out a theory called evolution by natural selection. Okay. What he showed was that if there is a thing that you see in organisms in nature, it came about for a reason, not imposed from outside, but affected slowly so that that organism had that for a purpose to survive better, okay, to reproduce better, to do something that was a little bit better than everybody else, to outcompete in the natural environment. Okay. So let's give an example. Mm, in Madagascar, there is an orchid that has like a 12-inch long channel. To get to the pollen of this orchid, something really thin has to be almost a foot long and get down the bottom. So little bees can't get there. Like if you have a bee that's like pollinating a flower or something, you can't actually get down to the pollen and to do those things that you would otherwise do. Okay, so when Charles Darwin found that out, he hypothesized he the natural selection thing, right, by evolution. So he came up with a prediction. He said, if my theory of evolution by natural selection is correct, then there must exist an insect of some kind that can actually reach down a foot with a tongue or some other appendage or something like that into a little narrow part of this flower in order to pollinate it. Otherwise, that flower simply wouldn't exist, right? And people are like, you're crazy. There is no such animal. There's no such insect that has a foot long tongue that can actually get pollen from or nectar or whatever from this deep channel in this flower. But guess what? Experiments were made. Very, very sensitive cameras, long after Darwin's time, were put in place and watched several of these things in the wild at night. And over time, sure enough, a giant moth, which people had never seen before, right? Never known to look for them, like moth, like the size of your hand, kind of flew up to these flowers and extended a foot long proboscis, fancy word for nose slash tongue, whatever, right? Extended it down and actually was able to get the nectar and thus pollinate this flower. That's amazing. Darwin, as far as I know, never lived to see one of them. But there they were. They existed. He predicted it, and it could have been false, easily falsified. If people looked and looked and looked and never found it, then his hypothesis was incorrect. But lo and behold, it was confirmed. And so that's an example of evolution by natural selection and how it works so well. But then people started thinking more deeply, right? Over the course of decades, evolution by natural selection was tested over and over and over again and shown to be true, correct, confirmed, even though people thought, geez, that's nuts. How is that possible? Well, eventually people started thinking of exceptions. They said, you know what, for example, if you have really, really good evolution by natural selection, then in any given ecosystem, like say a field somewhere in England, okay, you will have exactly one species of cricket that's really, really good, right, at eating stuff. You have exactly one species of bird that is really good at eating that cricket. You have exactly one species of hawk that can eat that bird. So why do we have all this variation in our society, in our nature, right? It doesn't make sense. That's a challenge to evolution by natural selection because you have all these different things. And it took many, many decades after Darwin's death before scientists figured out. What happens is that evolution by natural selection isn't just a matter of whether or not you are the most powerful cricket or the most effective bird, but whether or not your species can survive more generations. Make sense? So it doesn't have to be that you are super cricket. It just has to be that, if I have a gazillion cricket kids, then even if like a whole bunch of us die out because we get eaten or we're not as good at getting food as the other cricket, my species will survive because there are so many of us that we can't all be eaten, that we can't all starve, that some of us will go on. And in fact, we will continue to multiply and increase. So that's an example of a small theory, right? The original evolution by natural selection with seeming holes in it, but showing that evolution by natural selection is actually much bigger. There was a lot more going on in there than people thought. And that is the way that scientific theories progress. They get better, they get richer, more and more stuff shows up. Make sense? And this is the second and final point that I will make in addition to this original structure, right? Remember all this stuff. Yeah, oops, this way, right? Facts into laws, data into laws, creating hypotheses. Test the hypotheses. If they are not correct, try again. If they're correct, scientific theories. If they don't get tested or if they're untestable, it's an unscientific theory. These two things are separate. But what if people try to combine them? Herein lies the potential danger of science and non science intermixing in an inappropriate way. The term is pseudo-scientific theory. Pseudo meaning fake, right? Those of you who have seen uh, biological stories, like amoebas, right? They have pseudopods. They have fake feet that kind of stretch out and then engulf the poor euglena or paramecium, right? Or if you play Pokemon, there is actually a Pokemon named Pseudo-Udo. Yeah, fake tree. Anyway, different story. Pseudo-scientific theories, they are dangerous, that you don't want. What happens is that people who wish to push or wish to believe unscientific things and want other people to believe them, they use the language, the cloak of science to disguise the fact that their information is actually pseudo or not scientific. It's totally okay to say, look, my theory is unscientific. I'm going to live it that way or not. But when you try to pretend that something is scientific, or you try to convince other people that's scientific and therefore has a credibility of scientific falsification, but in fact it doesn't, that's when you run into trouble. So in the olden days, like astrology, right, was the best people could do. Thousands of years ago, they had no idea how the planets orbit the sun and things like that. Newton's laws of motion wasn't part of their thought process. So they guessed. Their hypotheses were unscientific. But then what happened was when people figured out the scientific results, right? People who originally thought, oh yeah, the astrology is what works, explains things and makes predictions and so forth. Turns out that, well, no, it's not. It's not scientific. So it's a non-scientific theory. And then astronomy is like scientific. That's an example, right? However, there's still people today who sometimes they try to just entertain you, like in the newspapers. Sometimes they actually try to like rip you off and like say, well, I can predict the future for you if you believe me. And they couch their fake stuff, their non-scientific stuff, in like scientific language. Oh, Jupiter is in the seventh house. Where the moon is in the seventh house. No, Jupiter aligns with Mars. And these are all these kinds of different things. Well, Mercury is in retrograde, and those are supposed to explain why, through these cosmic physics ideas, physical science theories that have been shown to be true. Now they're saying, oh, that's why tomorrow you should give me money because, then I'll be able to support you and protect you from evil spirits or something like that, right? Or that, tomorrow's a good day to go on a date and come to my restaurant or something like that. So you have to be careful about pseudoscience. It happens all the time. It's pretty much everywhere. In the health sciences, it's particularly prevalent. Pretty much every nutritional supplement ad that you watch on TV is pseudoscientific. Think about it. Some buff former athletes like, yes, if you eat this nutritional supplement, you will be tough and strong like me, even decades after you retire, because, yeah, eat this stuff. Mm. And and then underneath there's a little tiny thing that says these statements have not been approved by the FDA, right? The FDA is the Food and Drug Administration. It is specifically an agency that is tasked with making sure that your hypotheses are tested and that scientifically we have evidence to show that your stuff works, right? The FDA can be maddening to some people. They're really upsetting because, like, you make a vaccine. Why do you have to wait months for the FDA to approve it? Right? It's because the FDA is going through that whole process, looking at data, looking at the laws, looking at your hypothesis, seeing if your observations and your experiments or even your simulations in some instances, can actually do what you say it does. And they will attempt to falsify only when they are satisfied that scientifically speaking, this drug or this supplement or this method or this instrument is doing what you say it's doing and it's not dangerous. Only then will the FDA give approval. That's what it's supposed to do. And that's why it takes forever. Sometimes it's very frustrating. But when it says these statements have not been approved by the FDA, what is it trying to tell you? They're basically saying we are being pseudoscientific. We are using these words: alpha lipoic protein gluconate supercombinida nugenic whatever, right? I don't want to use any brand names, but the whole point is all these different words are supposed to make you think this is serious. And they say studies have shown, this has been proven, whatever. But the studies aren't scientific. They haven't been tested. They're not true falsifying things. They're just kind of there, right? Those you got to watch out for. You got to be careful. And you got people who say, well, if you get this particular medical thing happening, then you're going to have chips implanted in you, or you have 5G coming out of your ears, or something like that. Those are all just words thrown together to sound sophisticated, to sound scary, or to sound one way or another to convince you one thing or another. But the science of it, the actual falsification, the actual testing, that's not there. That's pseudoscience, and that's dangerous. And that has led to all kinds of suffering, all kinds of wasted money, wasted time, or even just, you know, life being not as good. So understand scientific theories versus non-scientific theories versus pseudoscientific theories. Scientific theories have gone through a process. They may not be great, they may not be right, they may not be complete, but they have gone through a process. So you have some sense of what you can expect from them, and then you can ask questions about them and test them, things like that. Non-scientific theories. I don't have an envelope that says non-scientific theories, so hang on. I'm going to put the word non here. Not the bread non, which I like very much, by the way, but this is non-scientific theory, right? Is not tested, or maybe untestable, cannot be falsified, or just hasn't been falsified yet. The non-scientific theory might be correct, but it is a thing that has not gone through all of that extra step of confirmation. And then there's the pseudoscientific theory, the thing that claims to be scientific by couching it in scientific terms, but is in fact a non-scientific thing, and in fact might even be dangerous, might even be designed to deceive you, designed to cause your life to be not as good as it otherwise could be. Right? So that's science. It's complicated, it's messy, there's lots of stuff involved, right? And then the hierarchy of understanding and knowledge is much more complicated than you might expect. But it's worth it, because when you organize all this information in a way that makes scientific sense, then you're on your way to learning more about how the world works, how the human body works, how the universe works. And this is where we get advancements to our lives and improvements to our daily and our societal lives. That's the end of lecture 2. Thanks so much for watching and listening. If you have any questions, of course, ask, and make sure to fill out and finish out the study guide. Okay? You have homeworks and things like that. Pay attention. Anything you want. Any questions you have, ask them at the appropriate time. I look forward to answering them if I can. Thank you again so much. Bye. Till the next lecture.